Hello everybody, welcome back to Calculus 1 online at Frederick Community College. In this video, we will continue discussing limits at infinity, and we will focus our discussion on transcendental functions. Let me give you just a quick reminder of what transcendental functions are. So trigonometric functions such as sine of x, cosine of x, and here you see a graph of sine of x in the upper left corner. Inverse trigonometric functions, and over here on the right you can see arc sine function. Logarithmic functions and exponentials, and they're graphed down below. So those are the four types that we will discuss in our class. Now there are other functions that are also considered transcendental functions, but we will only focus on these four types. And you might have to review some of the basic properties of these functions before attempting to compute limits. Now let's go ahead and do a very quick review of the main properties of trigonometric functions. So here you see the graphs of sine, cosine, tangent, cotangent, secant, and cosecant of x. And this is something that we've learned in our previous math class, whether it was pre-calculus or college algebra with trigonometry. So what we need to know from these graphs is how to determine what the domain of each function is and range. So for example, sine of x, what would be the domain of sine? By looking at this graph in the upper left corner, we can say that sine's domain is all real numbers. Okay, we can plug in anything we want for that x, and the range will be between -1 and 1, right? So the range is restricted, and it's right here. You can see how your graph goes up to 1 and down to -1, and that's where that curve lives. Okay, what about tangent? So let's shift our focus to tangent. Tangent is down below, and we can see that tangent is not defined for every value of x. We know that because tangent is sine over cosine. So all the values where cosine is equal to 0, we need to exclude those values from the domain. So that would be -3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and so forth. You know that there are infinitely many points where tangent is undefined. So on the graph, that's your vertical asymptote. Okay, so that would be the domain, excluding all of those odd multiples of 3 pi over 2. Okay, what about range? Range would be all real numbers, right? And how do we know that? Well, if you take a look at the graph, then we will see that it covers the entire vertical line, right? Okay, so the graph shows us domain and range. Okay, what about secant of x? Similarly, by looking at the graph, we can say some things about the domain and range. Okay, secant is 1 over cosine. So again, we're excluding same values as for tangent, right? So -3 pi over 2, pi over 2, and so forth. All of these numbers we got to exclude from the domain, and that's where we have vertical asymptotes. Okay, what about range? Well, range would be everything except the region -1 to 1. So let me highlight the range. So that would be from -infinity to -1, and then we have a gap here, and then from 1 to +infinity. Okay, so these are the things that we will need to keep in mind as we approach limits. Okay, I'm going to let you go through a similar analysis for the other three functions. So cosine, cosecant, and cotangent. I would take your time and analyze the graphs, review these properties, and if you need to have this cheat sheet in front of you as you work through the problems, that's completely fine. Okay, so something to keep in mind. Make careful notes with the information that you will find useful for computing these limits. All right, so now that we've had our quick review of trig functions, let's go ahead and compute limits at infinity of some of the trigonometric functions. Here we ask to compute the limit of f of x as x goes to positive infinity and negative infinity of the function 2 cosecant of 7 over 5x. So how do we solve this problem? First, I'm going to analyze the behavior of 7 over 5x. And we know how to compute those limits. So the limit as x goes to positive infinity of this expression is 0. And we can say a little bit more about it. We say that 7 over 5x goes to 0 on the right as x goes to positive infinity. What does that mean? If I were to create a table where x gets really big with positive values, then f of x would get really small but also positive values, right? That means we're approaching 0 on the right side. Similarly, for x going to negative infinity, the limit is still 0, but now we're approaching 0 on the left. So here, if I were to create a table where x would go to negative infinity, the values for f of x would also be negative, but in magnitude, they would get very small, so we would be approaching 0 on the left. Okay, so now we can take a look at the graph of cosecant and see what happens as we approach 0 on the right side. Well, what happens here? So approaching 0 on the right side, so that would be over here. We're coming to 0 from the right. What happens to the branch? The branch of the graph goes up to infinity. Okay, and that's why we have limit as x goes to infinity of 2 cosecant of 7 over 5x is equal to infinity. All right, now what happens as x goes to negative infinity? Well, as x goes to negative infinity, okay, we're approaching 0 on the left. Okay, so we're coming from this side right here. And notice what we have for the graph of cosecant. Okay, the cosecant is going down to infinity. Okay, so that's negative infinity, right? So limit as x goes to negative infinity of 2 cosecant of 7 over 5x is negative infinity. Now, this graph right here represents the graph of just cosecant of x. Okay, you could also graph using Desmos 2 cosecant of 7 over 5x and confirm that these are the limits. Okay, remember limits are about behavior of functions. So that is your first problem. You might encounter something very similar to this problem on your homework. Now let's take a look at a second problem. Same idea, we would like to compute the two limits. Now we're working with 2 cosine of 2x to the fourth. Okay. Same principle. I'm going to first compute the limits of the argument of the function. So here I'm going to work with 2x to the fourth power. Okay. Now this is a polynomial of even degree with the positive leading coefficient. We know what the end behavior of such functions is, right? So you can think about a parabola that looks like this. So both branches going up to infinity, and that's where these limits come from. So limit as x goes to positive infinity of just this polynomial, right? What is it? It's positive infinity. Okay, and then limit as x goes to negative infinity of just this polynomial expression is also positive infinity. And once again, this is justified by the end behavior of polynomial functions, which we have discussed in our previous lecture. Now, this is for the argument of 2 cosine, right? So what happens to 2 cosine of 2x to the fourth? Okay, so remember, this goes to infinity, and also this goes to infinity. Okay, both arguments. But if we take a look at the graph of cosine, okay, as x goes to the positive side, right, to positive infinity or negative, our graph just oscillates, right? It never approaches any fixed value. It just keeps bouncing up and down between -1 and 1. Well, in this case, because we have 2 over here, okay, we're going to have oscillation between -2 and 2. However, we're not going to have a limit. Okay, why not? Because this function cosine, okay, what type of behavior does it exhibit? It just oscillates infinitely. Okay, we're not going to get a number that is going to be approaching. So you can also graph this with Desmos to confirm. Okay, you will see that the graph just oscillates. All right, so that's why we would say does not exist. And then in Desmos, not in Desmos, on Newton Alta, once you come across a problem of this type, I believe you will need to enter something that looks like this. It will be one of the options to enter for the limit does not exist. Okay, so these are your first few problems of computing limits at infinity of trig functions. Now let's switch our focus to inverse trig functions. This is a topic that's typically not very intuitive to students, so I strongly recommend having this type of table or cheat sheet with all of the inverse trig functions in front of you so you can easily identify their domain and range. So here you see arcsine, arccosine, arctangent, arcsecant, arccosecant, and arccotangent functions. Okay, so let's go ahead and review just one of them. Let's take a look at arctangent. So this is the function in the upper right corner. And by looking at the graph, we see that the domain of this function is all real numbers, or from negative infinity to positive infinity for x. And that is indicated by the fact that this graph goes all the way to the right side, right? So positive infinity, okay? And on the left, this graph keeps going, so that's negative infinity, okay? We can plug in anything we want for x in the arctangent function. Now, what about range? The range is between -pi/2 and pi/2, not including these endpoints. Notice that we have a strict inequality, and that is indicated by these horizontal asymptotes, right? So the graph is approaching pi/2 and -pi/2, but it's never going to reach it. Okay, so this is just a quick review of arctangent. You can see a similar analysis can be done for the rest of these functions. Okay, and again, I do not expect you to just memorize these. As you work through the limit problems, just have a table like this in front of you so you can refer to it and extract this information easily. All right, so let's solve some problems where we compute limits at infinity of inverse trig functions. And the first problem says f of x is equal to tangent inverse of 6x plus 8x cubed. Okay, so the strategy will be the same. First, let's take a look at what happens to the argument of this function. And what do I mean by that? That is the expression inside the tangent inverse function. So this is a polynomial of odd degree with the positive leading coefficient, we know how this type of function behaves. So that would be similar to how x cubed behaves, right? So as x goes to infinity, the limit of 6x plus 8x cubed is positive infinity. Okay, and what about the other limit? As x goes to negative infinity, the limit of this cubic polynomial is negative infinity. Okay, so that is how the argument of our function behaves. And now we take a look at the graph of tangent inverse and see what happens to tangent inverse as the argument goes to infinity and negative infinity. Well, what happens to tangent inverse as the argument goes to positive infinity? Well, we see that the upper limit is pi over 2, and that's where this value comes in. Okay, so the limit as x goes to infinity of our function f of x is positive pi over 2. What happens as x goes to negative infinity? So this is us going to the left. Okay, the graph of our function goes down to the left, but it does not go to negative infinity. Okay, there is a lower limit, and that would be negative pi over 2. Okay, so I hope now you see what I mean by referring to the graph of the original inverse trig function. Okay, once you figure it out what happens to the argument of the function, then just go back to the original inverse function and see how it behaves. Now, of course, you can always take your tangent inverse of 6x plus 8x cubed and plug it into Desmos to confirm that that is in fact true, that that's what happens to this function at positive infinity and negative infinity. Okay, let's take a look at the second problem. Here we have f of x is equal to cotangent inverse of 9x plus 2x cubed. Okay, so you can already see that the argument of this function behaves exactly the same, right? So we have a cubic polynomial with a positive leading coefficient. So we can say right away that the limit as x goes to infinity of this polynomial is positive infinity. Okay, and as x goes to negative infinity, the limit of this polynomial is negative infinity. And again, this is related to the end behavior of polynomial functions, which we have discussed previously. Okay, so now that we know how the argument of this function behaves, we can take a look at the graph of the original cotangent inverse. Okay, so it is right here on the right side, and see what happens here. So as x goes to positive infinity, this branch goes down and then it approaches 0, right? So here we have a lower limit of 0. So that's where this number comes from. Okay, what happens as x goes to negative infinity? So x goes to negative infinity, the branch goes up and approaching pi. Okay, so that's where this limit comes in. And as always, you can just take this whole function, cotangent inverse of 9x plus 2x cubed, plug it into Desmos, confirm that your upper and lower limits will be pi and 0 respectively. Okay, so this is how we would approach computing limits at infinity of inverse trig functions. Let's do a very quick review of logarithmic and exponential functions. So here on the left side of the slide, you can see a sketch of the exponential e to the x. And from here, we can see that the domain of this function would be all real numbers, right? So that would be from negative infinity to positive infinity for x. And for y, we have a restricted domain, so that would be from 0, not including 0, to positive infinity. We can see that the graph of this function goes through the point 0, 1, and it is an increasing function. So just a couple of properties that we can identify just by looking at the graph. All right. On the right portion of the slide, we see a function f of x is equal to natural log of x, which is the inverse of the exponential. And notice what happens here. What is the domain of this function? The domain of this function is all values that are greater than 0. So from 0 to infinity, that's going to be the domain. Okay. The range is all real numbers, right? So that would be from negative infinity to positive infinity. All right. And we're going through the point 1, 0. All right, so here you can see a couple of connections. The domain of the exponential is the range of the logarithmic, okay? And also the range of the exponential is the domain of the logarithmic, which is not surprising at all. This is just a property of inverse functions. Okay, so it is good to have a pretty good idea of how these functions behave, what their domains are, what their ranges are. Now let's take a look at some problems where we're asked to evaluate limits at infinity of logarithmic functions. First, we would like to compute the limit as x goes to infinity of the function natural log of 4x squared plus 8 minus natural log of 7x squared minus 7. So how do we approach this problem? The first thing we're going to do is combining these logs. So you see how I rewrote my function as natural log of the rational expression 4x squared plus 8 over 7x squared minus 7. And now we know how to compute the limit of that rational function. We have two polynomials of the same degree. So we have a quadratic polynomial on top and quadratic polynomial on the bottom. We know how to compute that limit. We take the ratio of their leading coefficients. So this is where 4 over 7 comes from. And now we compute the limit of the natural log of that expression. So limit as x goes to infinity of f of x is just natural log of 4 over 7. And now I'm going to use Desmos to confirm my result graphically. So I'm graphing my function, the original function over here. I just plug it in just like that as the difference of two logs. And I also graphed y equals to natural log of 4 over 7. And it's indicated by this horizontal line, okay? And you can see that the right branch gets closer and closer to this horizontal asymptote. So the limit as x goes to infinity of this function is indeed natural log of 4 over 7. Okay, so that's your first example. Let's take a look at the second example. Looks very similar, but you will see how it will be different. Okay, once again, we're asked to compute just one limit as x goes to positive infinity. And now the function is natural log of 7x cubed plus 10 minus natural log of 9x squared plus 6. Okay, let's see what happens here. The first step is the same. I'm combining my logs. So now I'm working with natural log of a rational expression. And what is this expression? It is 7x cubed plus 10 over 9x squared plus 6. Now notice the limit of this rational expression is positive infinity as x goes to infinity. And I am skipping some steps here. But what can you do here? You can divide both top and bottom of this expression by x squared, and you will see that you're going to get infinity on top and a finite number on the bottom. So as x goes to positive infinity, this function also goes to positive infinity. Okay, and now here is the graph of our function f of x, confirming graphically that the limit as x goes to infinity of f of x is also infinity. Okay, so notice that for the first problem, our limit exists. It's a finite number. Okay, and then for the second problem, the limit does not exist, right? The function goes up to infinity. From the graph, it looks like it doesn't go to infinity very fast, but it certainly grows to infinity. Let's take a look at the last set of problems where we're computing limits at infinity of exponential functions. So for the first problem, we're asked to compute the limit as x goes to positive and negative infinity of the function negative 4 plus 2e to the negative x over negative 3e to the negative x plus 1. So let's see how we approach this problem. So first, I'm going to compute the limit as x goes to positive infinity. Notice what I'm doing here. I rewrote my numerator as negative 4 plus 2 over e to the x. And denominator is 1 minus 3 over e to the x. And I'm doing that because now it's easier for me to see what happens to this function as x goes to infinity. So this term right here, 2 over e to the x, that goes to 0. And then the term in the denominator, negative 3 over e to the x, that also goes to 0. So we are left with negative 4 over 1. So the limit as x goes to positive infinity of this expression is negative 4. Okay, now for the limit as x goes to negative infinity, I'm going to use the trick of multiplying my function by e to the x. And here is why I'm doing it. Notice that if I do e to the negative x times e to the positive x, this is the same as e to the x negative x plus x. So that's, of course, is 0. And e to the 0 power is just 1. So now I have this expression right here. And once I evaluate this for x going to negative infinity, this term goes to 0. E to the x also goes to 0. So we're left with 2 in the numerator, negative 3 in the denominator. So the limit as x goes to negative infinity is negative 2 over 3. Okay, and now I'm going to use Desmos to confirm this result. So I'm graphing my function f, and I also graphed two horizontal asymptotes. Okay, y equals to negative 2 over 3. So that's this asymptote right here. And notice that my left branch goes to this asymptote, right, as x goes to negative infinity. Okay, and then the second horizontal asymptote is right here. So this is y is equal to negative 4. The right branch of the graph is approaching negative 4 as x goes to positive infinity. So this graph confirms our computations. Okay, last problem for today's lecture. Here we're asked to compute the limit as x goes to positive and negative infinity of the following exponential function: 3e to the x minus 6 in the numerator, 6e to the x minus 1 in the denominator. The approach will be very similar. So here is the solution. Okay, I'm first going to compute the limit as x goes to negative infinity. Okay, what happens to these expressions? So this goes to 0, this goes to 0. We are left with negative 6 on top, negative 1 on the bottom. So the limit as x goes to negative infinity is just going to be 6. Okay, what happens to this function as x goes to positive infinity? Notice the trick that I'm doing here. I am multiplying by e to the negative x over e to the negative x. This is equivalent to multiplying by 1. Okay, completely legal operation in mathematics. And once we do this, now I can evaluate my expression as x goes to positive infinity. So this goes to 0. This expression goes to 0. We have 3 on top, 6 on the bottom. 3 over 6 is 1/2. All right, and now I'm going to graph it. Okay, here is my graph with 2 horizontal asymptotes. Okay, so y is equal to 6 over here. Okay, notice as x goes to negative infinity, I have this branch approaching the horizontal asymptote y is equal to 6. So that is my first limit. Okay, and then the second asymptote is y is equal to 1/2. As x goes to positive infinity, the branch of our graph is approaching that value. So that is our second limit. Okay. All right, so we're going to go ahead and stop right here. Thank you all for watching, and I will talk to you next time.